David did his PhD last year, 2021, at the UW, University of Waterloo, and at Parameter Institute, I think, right? So Rob was your supervisor.
Yeah.
Also Lucian?
Just Rob officially.
Yeah. Yes, okay. Yeah, and now you're a postdoc at the ICTQT in class. And I also have to look up what it stands for. It's International Center for, what is it? Theory of Quantum Technologies.
There you go.
Okay. Yeah. Okay. Yeah, and we will hear about macrorealism as strict classicality in the framework of GPTs.
Cool. Thanks, Marcus, and thanks you all for being here. It's been a really nice visit and very inspiring. It's kind of impressive to see this audience at just like a research visit to a university. So, Vienna's the place to be. Although we're growing here too, much smaller than you guys, but hiring more all the time. So as Marcus said, I work in Gdansk with John Selby and Anna Belen-Sains. And I'm going to be telling you about a topic that I think is particularly fun to talk about because it's kind of contentious. There's a lot of people who love it, and there's a lot of critics. And I'm going to try to kind of disagree with both of them. So in particular, I'm going to start by telling you why the traditional notion of macrorealism has some problems and needs to be kind of reimagined. And the proposals for how to experimentally falsify it have even more serious problems that we need to reconsider. And many of those criticisms have already been made, but I'm going to bring some new ones as well. But then I'm going to argue that we can fix those problems, both with the definition and with the experimental proposals. We can use kind of modern quantum foundational tools to fix those problems. And once we do that, we're left with a totally reasonable notion, which can be falsified in some theory-independent ways. So in other words, I'm going to try to make macrorealism great again. So the original paper on macrorealism was about 40 years ago, where Leggett and Garg introduced this notion. And they start out by saying, despite 60 years of schooling in quantum mechanics, most physicists have a very non-quantum mechanical notion of reality at the macroscopic level. And I think we all would agree with this statement. At the macroscopic scale, so Leggett and Garg go on to say, objects in the everyday world of our immediate experience, things like tables and chairs, have definite states and can be observed without disturbance. But most of us would agree this is not a reasonable description of the microscopic world. So the question Leggett and Garg wanted to address is, does quantum theory break down in the macroscopic limit? Could it be that it's just the wrong theory? Or should we understand that somehow the classical world emerges from quantum theory in an effective way? This was the question they wanted to probe. And clearly, the answer to this question will depend on your interpretation. So if you believe in collapse theories, you'll say, yes, quantum theory is just wrong at the macroscopic limit. But other interpretations might give different answers. And Leggett and Garg's goal was to answer this question, or to address this question in a way that looks to experiment and uses rigorous no-go theorems to answer the question. So traditionally, how have people tried to address this question? Well, they'll take some macroscopic object and they look for quantum interference phenomena. So Vienna has a lot of nice work in this area, for example. So here's a plot from a relatively old paper by Marcus Aspelmeyer, where you take kind of larger and larger objects and you keep looking for evidence of quantum interference. But Leggett and Garg were not satisfied with this kind of approach. They said, even if you can verify the predictions of quantum theory, some interference phenomena, for really macroscopic objects, that doesn't necessarily rule out a competing classical theory. So they wanted a formal proof, a kind of no-go theorem that says, if you've verified the quantum predictions, then you've moreover ruled out some competing class of classical, or what they called macrorealist theories. And it's not unreasonable to demand this extra level of rigor, because as we saw in Rob's talk earlier this week, I thought I had a slide for that, apparently not. As we saw in Rob's talk earlier this week, a lot of basic interference phenomena can be reproduced in a model that's local and non-contextual, and so can reasonably said to be classical. So Leggett and Garg's approach was the following. They said, first, let's give a precise definition of some class of theories, which they called macrorealist. And then let's devise an experiment that's capable of deciding whether this notion is correct or not. And this is going to be the outline of my talk. The first half is about the definitions, the second half about experimental tests, And in both halves of the talk, I'll start with the traditional way that things were done, and then I'll criticize that, and then I'll give what I think is a better definition and a better proposal for how to test these notions. Okay, so let's start with Leggett and Garg's definition of macrorealism. So it's composed of two parts. So the first assumption they called macrorealism per se. So this is like the essence of macrorealism. It says a macroscopic object which has available to it two or more macroscopically distinct states is at any given moment in one of those states, in a definite one of those states. And their second assumption was called non-invasive measurability at the macro level. So it's possible in principle to determine which of these states the system is in without any effect on the state itself or the subsequent system dynamics. So I'll start by noting that this definition refers to a notion of macroscopic. And people don't always agree on how we should define macroscopic. It's a kind of slippery topic. But in some sense, that question is not going to be relevant either to anything Leggett and Garg did or to anything I will say, because this definition of macrorealism is kind of agnostic. Pick your favorite definition of macrorealism, and then just apply this definition with respect to that notion. So in other words, you can test these assumptions even on a photon. Just nobody's going to be surprised if you violate these assumptions on a single photon, because you don't expect it to sort of always be in some macroscopically distinct state. It's only when you do this experiment with something large, like a marble or a chair, then you'd be surprised if you violate these assumptions. And different people might be impressed for the marble or the chair. But once you get macroscopic enough by your favorite definition, that's when you should be interested in probing this conjunction of assumptions. So that's convenient because it means we don't have to have a long discussion about how you or someone else prefers to define macroscopicness. So let's turn now to clarifying this definition of macrorealism. So there's a lot of kind of things that could be said about the motivations and the conceptual framing of the definition, and a lot of the literature has kind of discussed these points and argued about them. I'm going to try to focus on just one or two main points, but if you want a more thorough analysis, there's a nice 45-page paper here by Owen Moroney and Chris Timpson. It's a very nice analysis, and I recommend it. For our purposes, the main problem with this definition that I want to highlight is that it refers to a notion of a state, and it doesn't ever define what this notion means. Typically, the notion of a state comes in some particular conceptual framework. And Leggett, even in his subsequent writings, never really says precisely what he means by state here. So if you're working in quantum theory, the notion of state would be a quantum state. But if you're working in the ontological models framework, the notion of state might be some ontic state, some hidden variables describing the properties of the system. Maybe you could have some more general kind of operational state in a framework for operational theories. But until you specify which one of these you have in mind, this definition is hard to parse in an unambiguous way. And in fact, a lot of the argument in the literature can basically be seen as different authors reading different notions of state into the definition and then talking past one another. So if you go and you read all of Leggett's work, I think I came to the same conclusion that Timpson and Moroney came to. So I think they summarized it nicely when they said the following. So Leggett and Garg's discussion strongly suggests that their background framework is simply quantum mechanical Hilbert space states. Macroscopic states are the quantum states that one would assign to macroscopic or collective degrees of freedom. So for example, in a superconducting qubit, one does not trouble to assign a massively entangled multiparticle quantum state to the enormous number of individual charge carriers. Rather, you just assign a single state to the collective degree of freedom, the direction of the current. So +1 or -1. These are effective quantum states, or they're quantum states on some effective degree of freedom. And the content of macroscopic realism is then that the only permissible states of the qubit are the quantum states +1 and -1 and statistical mixtures thereof. So the point of macrorealism is to disallow quantum superpositions of these two privileged states. So in other words, according to this reading of Leggett and Garg's notion, the notion of state is basically the quantum state, but not all quantum states are allowed, only the diagonal ones. And in a much later paper, Leggett, here's just one quote of many I could give you to try to support this reading. So they say, in this quantum language, the predictions of a macrorealist theory are equivalent to those which follow from putting the off-diagonal terms in the density matrix to 0. So, yes?
Didn't anybody ask Leggett because he's alive? It's not that.
Yeah, I mean, there's many papers arguing back and forth about this notion, and so let me finish this slide, and maybe it will.
Doesn't make any sense when the guy's alive and can't answer the question.
I think I'll address this point. So on this reading, it's very simple, and it's like, yeah, why not just ask Leggett, is this what you meant, yes or no? And I think the point is, this is a very simple idea, but it's very hard to state without reference to quantum concepts. So they didn't want to commit themselves to this kind of reading because they're trying to imagine the whole hypothesis they want to rule out is a hypothesis wherein quantum theory is false at the macroscopic level. So they wanted to phrase their definition in a way that didn't make any reference to quantum-specific concepts. But 40 years ago, when they were doing this, they didn't have any frameworks for describing alternative theories in a way that didn't use quantum concepts. And now we have the language, I think, to avoid these problems. We can use the framework of generalized probabilistic theories, for example, to formalize what we mean by, quote, diagonal quantum theory in a way that isn't just take quantum theory and apply a superselection rule or something like that. So I suspect if you asked Leggett, you might first have to discuss with him. I don't know how familiar he is with kind of these tools we have to describe theories in ways that are agnostic to the theory. But to me, that is kind of the essence of why there's so much confusion around this. It's just because it was an idea ahead of its time a little bit. Okay, and I want to stress that this definition here, if you buy this reading, then this has almost nothing to do with realism. So you can have plenty of different realist understandings of quantum theory, even at the microscopic level, much less the macroscopic level, where things are not equivalent to diagonal quantum theory. So Bohmian mechanics or many worlds, they don't forbid quantum superpositions, but they're perfectly realist attempts to understand the world. And similarly, even if you do believe that there are no superpositions of macroscopic objects, you're not forced to be a realist. You can be operationalist if you like. So this idea that they called macroscopic realism, it's neither necessary nor sufficient for realism. So it's not really a good term. And we kind of all know what diagonal quantum theory is. It's a notion of classicality, right? It's the strongest notion of classicality. Everything's diagonal. States are perfectly discriminable. You can do measurements without disturbance. It's a really strong notion of classicality. And it makes sense that this would be their hypothesis if they're trying to describe everyday objects in our immediate experience, tables and chairs. Their hypothesis is that quantum theory is strictly wrong, that this isn't just some effective emergent diagonality, but that really there's a different theory, which is strictly diagonal, describing these macroscopic objects. So that's the notion that they were trying to capture, as far as I can tell. And this all accords pretty much with Timpson and Moroni's analysis, I think, as well. But what I'd like to do now is I'd like to kind of formalize this notion a little bit in the framework of GPTs. So just to remind you briefly how GPTs work, the content of a theory in a GPT is given by its convex geometry. And so for a qubit, for example, we have some state space and some effect space. The state space we're all familiar with. It's the block ball. The effect space is a four-dimensional object, so it's a bit harder to visualize, and we don't talk about it as much. But it's some kind of zonotope, and here's a three-dimensional slice of what that looks like. And in a GPT, the states and effects are just real-valued vectors living in the state space and the effect space, respectively. So, the block vector in the qubit is the state. And then similarly, you have some effect vectors. And if you want to compute probabilities in the theory, you just take dot products of these vectors. And so, as I said, the content of different operational theories is encoded in their convex geometry. So for example, you can see just from the convex geometry of this qubit that there's no state which reaches values 1, 1, 1 on the three x, y, and z measurements, for example. So there's an uncertainty principle which constrains the joint predictabilities of these three measurements, Whereas in this GPT, we can get all the way out to this point here, 1, 1, 1, so there's no corresponding uncertainty principle. So you can kind of read off the operational properties of the theory from the geometry. So many other GPTs have been studied. We have like Boxworld, Spekens toy theory, maybe just some random GPT with no particular symmetries or interesting properties. But you can characterize the landscape of possible ways the world could be in this kind of operational framework. And so our question is, what does diagonal quantum theory look like in such a GPT language? Well, this answer is kind of well understood to people who know GPTs. They're known as simplicial GPTs. So for example, a classical bit embedded in a qubit, well, it's the diagonal quantum states. So you pick some basis, dephase all the states, and you end up with kind of two extremal states, which kind of correspond to the classical states, and then you have all the mixtures of those states. And similarly, you can talk about what happens to the effect space. In higher dimensions, a simplicial GPT is just a set of linearly independent vectors can define the extremal states of the GPT. So here we have a triangle, this triangle connecting these three vertices. In dimension 3, that's the simplicial state space. In higher dimensions, it's the generalization of the triangle. And the effect space is the set of all vectors whose inner product with the simplicial vectors is between 0 and 1, so valid probabilities. So it might help if I just add indices here, so we can choose a convenient coordinatization, and we can put these three vertices of the three-dimensional simplex at the three unit vectors in three-dimensional space. We have the completely subnormalized state here, 0. The normalized states all just lie in this triangle. So the subnormalized state space is three-dimensional, but the normalized state space lives in one lower dimension. And you can just see now easily that this is the set of all effect vectors whose inner products with these vectors is between 0 and 1. So this is what the three-dimensional simplicial GPT looks like. And such GPTs for any dimension are just describing classical statistical theories. You can view this as the theory of probability distributions over some fixed set of classical states. So here the classical states are the three vertices. You could call these the ontic states if you like. And the reason you can think of these as the sort of true states of the system is because every other point in the state space, so take this state for example, it uniquely decomposes into a set of weights onto these three ontic states. So this one has weights a half on these two ontic states, and it has weight 0 on this state. This point can be uniquely decomposed into a third, a third, a third. And every point in this state space is in one-to-one correspondence with a probability distribution over these three ontic states. That's what's special about a simplex and what's special about these simplicial theories. So every mixed state decomposes into pure states in a unique way, which means you can always imagine there's a true state of the system, and there's a unique interpretation of every mixed state as uncertainty about that true state. Another feature that makes these kind of naturally describing classical statistical theories, all logically possible measurements are physically possible and compatible in these strictly simplicial GPTs. So there's a single measurement which can exactly determine the state of the system, and moreover, typically it's imagined without any disturbance. You can't really read that off from the state and effect space, but this, if I defined everything for you in a more compositional way, this is also a property of simplicial GPTs. So for these reasons, we say that the simplicial GPT is the most classical GPT. I'll call it strictly classical. And as I sort of alluded to, more properly, if you're defining a GPT, you really want it to be a compositional theory. So I should really tell you about transformations and non-destructive measurements, and composition like a tensor product kind of rule, and so on. But for our purposes, we won't need that extra structure. If you're interested in it, you can find it in some of it in Barrett's original work and also in my work. So as I mentioned, the simplicial GPT contains a non-disturbing, perfectly informative measurement. This is just the formalization within the GPT framework of non-invasive measurability. So as Leggett and Garg tried to argue, this is a natural corollary of the notion of classicality they have in mind. I think that's fair to say. Transformations in the simplicial GPT are just stochastic maps on the vertices, but we won't need that, as I mentioned. Okay, so summary so far. Macrorealism is best described as the operational hypothesis that macroscopic systems are described by strictly classical GPTs, by simplicial GPTs. So in my view, this should be taken as the definition of macrorealism. I think it captures what Leggett and Garg were trying to say, but in a formal manner. And I want to note that Timson and Moroni's work already kind of moved their definition. They kind of argued this point. They kind of got halfway to this conclusion as well. They didn't actually use the framework of GPTs, but they, again, essentially were trying to get to this definition. They said you have some extremal macroscopic states and convex mixtures thereof, and essentially their extremal macroscopic states are just the vertices of the simplicial GPT. So they were also essentially reaching out for this definition. So there's some advantages of this definition over Leggett and Garg's, which is, well, first of all, it's precise. It's a precise notion of a theory and a precise notion of a state. And it makes explicit, I think, the fact that macrorealism is a notion of classicality, not of realism. So the framework of GPTs is a framework of operational theories. There's nothing particularly realist about it. It's not trying to provide some description of the true properties of the world and the hidden variables that describe what's going on, or anything so ambitious. It's just it's a strictly operational hypothesis. And moreover, these simplicial theories are kind of well characterized as complete theories with composition rules and dynamics and, I shouldn't say dynamics, transformations and non-destructive measurements and so on. So there's a lot more kind of that's known about them. There's a lot of known facts about simplicial GPTs. You can now use all those facts to kind of study macrorealism. You don't have to just look at, whether there are off-diagonal terms or something. You can consider properties beyond just the state space. You can look at the effects and the transformations and the composition rules. And just by virtue of putting this in the framework of GPTs, we can use all the tools that we know in the framework of GPTs. So we'll see kind of how these tools are useful to us in the second half of the talk. And finally, this approach allows us to directly make a connection between macrorealism and another notion of classicality, namely generalized non-contextuality. So that's going to be the last topic of the talk. All right, any questions so far before we move on to experimental tests? Cool. So the first proposal was in Leggett and Garg's original paper. They had a proposal for how you could go about experimentally ruling out their notion of macrorealism. And it's called the Leggett-Garg inequality, and it's pretty simple. So let's start by imagining a scenario. This is not what the scenario Leggett and Garg had in mind, but it's going to be useful for deriving the result. So this is kind of just a crutch for getting to the argument. So imagine you do 3 sequential measurements on a system, and you get outcomes Q1, Q2, and Q3. So there's only 8 possible sequences of outcomes that you could observe. If these are binary outcome measurements with outcomes, I'm labeling by plus or minus 1. And what Leggett and Garg observed is that there's only so many anti-correlations you can have between these 3 outcomes. So if I want to have all my outcomes be anti-correlated, we'll take the case where this outcome's plus 1. In order for this to be anti-correlated, this outcome of this measurement better be minus 1. The outcome of this measurement also has to be minus 1. So now we have 2 anti-correlations, but now you see that these 2 measurements are perfectly correlated. So by virtue of this kind of frustrated network, you can just see there's no way for all 3 pairs of measurements to have anti-correlated outcomes. So then they considered this kind of quantification of this anti-correlation, where all 3 measurements are done, so that's what the subscript indicates. So if you look at the anti-correlation between outcomes 1 and 2, 1 and 3, and 2 and 3, and you sum these together, ideally you'd like to have these be anti-correlated, so minus 1, minus 1, minus 1. You might think this could go all the way down to minus 3, but then you recognize this fact, and you see that the smallest you can make this quantity is just minus 1, and plus 1. So in other words, this quantity is bounded by minus 1. It's always greater than minus 1. So now let's move to the actual Leggett and Garg scenario, keeping this in the back of our minds. So the actual Leggett and Garg scenario considers 3 different counterfactual alternatives. So either you just do the first 2 measurements, or you do the last 2 measurements, or you do the first and the third measurement. And now you look at the same kind of correlators, but notice that now they're correlators in the case where only 2 measurements are done. So in principle, these 2 quantities don't have to be the same. Let's look at the first quantity, for example. So the only difference between these 2 quantities, so this quantity here is referring to this situation where M1 and M2 are done. Now clearly, whether or not measurement M3 was done can't disturb the correlations between M1 and M2 because it comes afterwards. So these 2 quantities, in fact, are equal. But if we now look at these 2 quantities, so this quantity here is in the case where M1 and M3 are done. Now, it does matter whether or not you do measurement M2 because that could disturb the outcome of measurement M3, which would in turn disturb the correlations between 1 and 3. So these 2 quantities, where this was defined in the situation of the previous slide where measurement M2 was done, these 2 quantities don't have to be equal. And similarly, these 2 quantities don't have to be equal because whether or not measurement M1 was done here can disturb the correlations between M2 and M3. So these 2 in general are not equal, but what Leggett and Garg assumed by their non-invasiveness assumption, they said, well, if these measurements are of macroscopic systems and you can do them in a way that doesn't disturb the system, then under that assumption, you can justify these 2 equalities, and then you get exactly the same bound for the joint statistics of these 3 counterfactual scenarios. And this is now what's called the Leggett-Garg inequality. And you can see explicitly this non-invasive measurability assumption that they used. So what they argued is that violations of this inequality on a macroscopic system, because only for such systems do you expect to be able to measure them non-invasively, but on such a system, if you violate this inequality, you've witnessed the failure of their assumptions of macrorealism. And I'll say more about this and criticize it in a minute. But first, I want to point out that if you buy their argument, then you should also buy a more clever argument that came afterwards by Clifton and a number of others and ultimately popularized by Koffler and Bruckner. So what Clifton noticed is that if you believe Leggett and Garg's assumptions and their arguments, then there's a much more simple and more general way of ruling out those same set of assumptions. So Leggett and Garg had to assume that you've built some measurement device that's non-invasive. And once you have such a measurement device, all you have to do is any other incompatible measurement after that measurement. And if you find that you have no disturbance on this measurement, as you've claimed you will, then you violated quantum theory. There's no way to do a non-disturbing measurement of 2 incompatible measurements. So this reduces the number of measurements you need in your argument to just 2, and the number of counterfactual scenarios also down to 2. You just have to do measurement M2 with and without the supposedly non-disturbing measurement beforehand. So this is a much simpler argument, and it was called no signaling in time, and some particular kind of equalities were derived by Koffler and Bruckner, who moreover noticed that any interference experiment can actually be understood in exactly this way, which implies that Leggett and Garg were too quick to say, oh, if you've gone and done a macroscopic interference experiment, you can't rule out macrorealism. In fact, you can. You just have to reimagine it properly. So, yeah, so I think that's kind of interesting that in some sense, if Leggett and Garg had thought a little harder about the exact same assumptions they had, they might have kind of recognized that you can take an interference experiment and turn it into exactly the kind of evidence that they were looking for. So it's kind of a cute coming full circle of their desires. So this is the kind of arguments, but in the literature, most, I would say, of the argument in the literature is about whether these tests of macrorealism are reasonable or not. And the arguments tend to center around this assumption of non-invasive measurability. So there's a whole bunch of works that have tried to criticize this. These are some of my favorites if you're interested. But in order to understand those criticisms and whether they hold water or not, it helps to think about 2 separate assumptions. So let's break non-invasive measurability in 2. I think this is important. So the first assumption is just, this is exactly word for word what Leggett and Garg assumed. They said non-invasive measurability at the macro level was it's possible in principle to determine which of the states the system's in without any effect on the state or the subsequent dynamics. But the second assumption I want to highlight, which is closely related, is the particular measurement that is actually implemented in your experiment is non-invasive. Now, these sound similar, but they're really completely different assumptions, both as a matter of logic and as a matter of practicality. So this is an assumption about a theory. It says what's possible in principle. But this is not an assumption about a theory. It's an assumption about a particular experiment. And Leggett and Garg need both of these assumptions. I don't think it was fair of them to say they were only using this assumption. I think they needed this assumption as well, at least in their experimental tests. And this is much stronger. And the criticisms of this first notion, so I think people in the literature have tried to criticize both of these assumptions, but I don't think the criticisms of this first assumption are fair. I think Leggett and Garg really wanted to capture diagonal quantum theory, these kind of the most macroscopic level of things, and I think it's reasonable to say, if I'm describing tables and chairs and things that commute, I can do measurements in principle that are non-disturbing. So I've tried to defend this part of their assumption, but it's this part of the assumption that people were really mostly upset about, which is in a real experiment, you're never going to have a perfectly non-disturbing measurement. And so, yeah, I think a lot of the argument in the literature is correctly complaining about this assumption here. Okay. So I've sort of already said this, but again, some of the criticisms have been arguing that non-invasive measurability has nothing to do with realism. That's true, but it does have something to do with this strong form of classicality. And non-invasiveness never holds in practice. That's, I think, the genuine problem. This has been called the clumsiness loophole in the literature. And Leggett and Garg tried to kind of get around this assumption, or they tried to respond to this criticism by introducing something by leveraging something that they called no-result measurements. And I'll just give you an example of a no-result measurement. Imagine you've got a double-slit interference experiment, so some particle going through these two slits, and you want to learn which slit the particle went through, but you want to do it in a way that's non-invasive. So what Leggett and Garg said is, if you put a detector in locally at one of these two slits, and you condition on the case where the detector did not fire, then you learn that the particle was at the other slit, and now just by some locality argument, well, this detector never was close to the particle, so it must not have interacted, so the particle can't have been disturbed by this detector. That's the argument. And now, of course, in general, this argument would be a bad one in a general theory. So, for example, if you believe that the wave function is ontic, like in Bohmian mechanics, the wave function is spread out at these two slits, so part of the wave function does interact with this detector. Maybe it induces a collapse or whatever, but if the wave function is ontic, then it will it can in principle be disturbed by this measurement, and then later it can affect the subsequent dynamics. And that's what happens in, for example, Bohmian mechanics. So they're not claiming that in every theory this is a non-disturbing measurement. They're just saying, if you believe macrorealism, then the only two possible states of the system are sort of at the upper slit or at the lower slit. Then under that assumption, that's when they claim this will be a non-invasive measurement. But I want to point out that this argument has some implicit assumptions. So first of all, it appealed to locality, which not everybody will buy. And second of all, it assumed that you know precisely what the macro states are here, that the only two possible macro states of the system are at the lower slit or at the upper slit. And that might seem like a reasonable assumption, but it forbids the possibility that there's any other properties other than the position of the particle that are relevant to this experiment. And you might, once you notice you could put a local phase shifter in one arm and change the statistics, you might take that as evidence that there must be some other properties other than the position. Because that local phase shifter, it's not changing the position, but it's changing the statistics. And indeed, we saw earlier this week an explicit kind of model where the states of the system are not just these two, not just this binary upper slit, lower slit properties, and we could reproduce the phenomenology of quantum interference. So in other words, these assumptions using no-result measurements to conclude that there's no disturbance, they can be made, but they rely on some theory-dependent assumptions about the number of macrostates and the nature of those macrostates. Namely, there's two, and they just correspond to particle positions. And because of these theory-dependent assumptions, these arguments that Leggett and Garg gave are not sort of on par with Bell arguments, which aim to be kind of totally theory-independent. So again, Timpson and Moroni have made a lot of these arguments in the past already, and they noticed that, or they summarized this as, if one happens to have certain views as to how the detailed physics of the interaction between system and measuring apparatus goes, then one might very well believe that one had a pair of measurements apt for null result, non-invasive measurement. But it could well be that one's model is simply wrong and that it's macrorealism which is at fault. And these arguments apply equally well to the Leggett-Garg inequalities and to the no signaling and time equalities, because both of those relied on this non-disturbance in practice assumption. But this brings us to our third proposal, which aimed to get around the problem of non-invasiveness. So they said, what if we don't assume non-disturbance? We just experimentally measure how much disturbance there is. Surely we can kind of quantify this and kind of numerically account for these problems. So let's take an example where we have two macrostates, two macrostates of the system, S1 and S2. And they said, imagine you found some transformation phi that does not disturb some particular effect E in some measurement that you can do for these two macrostates, S1 and S2. So in other words, you implement some measurement that has an effect E in it on system S. Then you implement it on the transformed system S, and you get the same statistics. Similarly, imagine you've verified the analogous condition for the second macrostate, S2. So if you've got this non-disturbance, property for phi on the effect E for the two macrostates, then it follows by linearity that the transformation phi doesn't disturb the statistics of the effect for any mixture of macrostates. So you can just kind of mix these two equations. So if you write any mixture of the two macrostates like this, and you apply phi, and you apply linearity, and then now you use these two conditions to say this is non-disturbing, so it equals this. This is non-disturbing, so it equals this. Now you find that on this mixture, the transformation phi is also non-disturbing. So then, if you find any state which is disturbed by this transformation on this particular effect, then you know that that state is not a mixture of the macrostates. So if you find a state which satisfies this statistical property, you know that V is not a mixture of S1 and S2. So that's the argument. And then the claim is just by exhibiting, so basically experimentally, you've got to find some states, transformations, and effects satisfying these conditions, but violating this equality. And once you've found all that, you've violated macrorealism. That's the claim. And I want to point out, before kind of criticizing this argument, I want to point out that, again, any proof of interference can be viewed in exactly this way. So those first two non-disturbance conditions, they call them the control experiments. So first you prepare the macrostate of being in the upper path and take the transformation phi to be a phase shifter and take the measurement to be post-selection on this outcome of this, pass the system through a beam splitter and then post-select on this outcome. So this is effect E. This is one of the two macrostates, and the transformation is a phase shifter phi. You see that this transformation phi here is not going to disturb the statistics of this effect because, it doesn't even change the phase of this particle. So you just get 50-50 statistics here, whether or not you have a phase shifter. Similarly, if you prepare this macrostate, where the particle takes the lower path, whether or not you do a phase shifter, you still just get 50-50 statistics here. So in both of these cases, you find the transformation phi doesn't change the statistics of E on these two preparations. But then you go and you find a different preparation, which I called V, namely pass the particle through a beam splitter. And now you find that the phase shifter phi does change the statistics of E. So this is all just kind of a concrete instantiation of the argument, the abstract argument on the previous slides. And I'll point out a little kind of nuance here that's easy enough to handle, which realistically, you'll never have that perfect non-disturbance equality, right? So in the paper that made this proposal, of course, they recognized this, and they said, you can just quantify how much disturbance there is for the two macrostates. So these won't be exactly 0, but you can pick some measure of disturbance and quantify these two amounts of disturbance, call them D1 and D2. And then by linearity, the same kind of linearity computation I did on the previous slide, the disturbance for a mixture of the macrostates will be given by the mixture of these two disturbances. And so in particular, it'll never be greater than the maximum of these two. So now we're saying in your control experiment, measure the quantities d1 and d2, and then find a state v which exhibits a disturbance greater than both d1 and d2. If you find a state v exhibiting disturbance greater than both d1 and d2, then you can be certain that that state v is outside the convex hull of these two states S1 and S2 that were prepared in your control experiment. And this statement here is completely correct. There's no issues that I have with this. But the catch here is, what you've proven is that the state v that you have prepared is outside the convex hull of your control states that were actually prepared. Those control states are never going to be exactly the extremal macro states. So this is the catch. And there's kind of two different ways of thinking about this loophole. So the first loophole is, well, what if you didn't even know what all the macro states were? So maybe you thought there were two macro states, and even if you could perfectly prepare those two states, it's possible that the state v is inside the macrorealist simplex, but it's just off in some dimension that you didn't recognize. So this is one loophole. A second loophole, which is maybe even more pernicious, is that in reality, you're never going to have prepared perfectly extremal states. So you've prepared these slightly noisy versions. So you're correct in the argument correctly deduces that the state v is outside the convex hull of these two states that you've prepared in your control experiment, but that doesn't mean they're outside the convex hull of the true macro states, S1 and S2. So you can also have this kind of example. And there's kind of a quantitative example I give in my paper, but I think I'm running over time for sure, so I'll skip that. So what's happened here is this proposal has no longer assumed any idealizations about the measurements being non-invasive, but now they've made it idealizations about the number and nature of the macrostates. You have to know exactly how many there are, and you have to be able to perfectly prepare them in your control experiment. And notice that it was exactly this same kind of conclusion that we were forced to when we thought about these null result measurements. In both cases, you kind of end up having to assume you know what the macrostates are, and also you have to be able to perfectly prepare them. And in those cases, yeah, then you can run these arguments, but we want to avoid these kind of assumptions. So you might think, well, okay, the problem here was that you had to have pure preparations. You'll never quite have purity, but you could just quantify how pure the preparations are. But now you're caught in a vicious cycle, right? How do you quantify the purity of the preparations? Well, you'd have to have some well-characterized measurements to do that. So then you could assume you have perfect measurements, then you can find the quantity. We're back to where we started. We're trying to make assumptions neither about the preparations nor about the measurements. We need some kind of self-consistent analysis that doesn't start with well-characterized preparations or measurements. And so this brings me to my proposal, which is exactly this kind of self-consistent approach. And it's really, in some sense, it's not at all my proposal. This notion of theory-agnostic tomography was introduced a ways back. So let's take a step back. Once you've recognized that macrorealism is an operational hypothesis about the GPT, just ask yourself, what is the sort of state-of-the-art method for determining the GPT describing a given system? And in particular, doing so without assuming you have well-characterized states or measurements a priori. Well, this problem has been solved in this paper here. And all I'm going to be doing is basically arguing that we should apply this proposal to figure out what the GPT describing a given macroscopic system is. Once you do that, you just check, is it a simplex or isn't it a simplex? So the input to this, actually, I'm running pretty far over time. Are people OK with that, or should I? OK. OK, great. So the input to this theory-agnostic tomography is you basically randomly sample a lot of preparations and measurements. They don't have to be randomly sampled, but you sample as many preparations and measurements as you can. And importantly, you don't need to know what those are. You just have to basically be able to do them repeatably. And you record the outcome probabilities for these preparations and measurements. And then you do an analysis, which I'll sketch in the next slides, which lets you compute the best fit GPT dimension, the GPT characterization of each of the preparations you did, and the GPT characterization of each of the measurements that you did. So these things come out of the analysis. They're not put in. And of course, then by the fact that you've now constructed a bunch of GPT states and effects, that forms an inner bound on the GPT. And if you do enough of these, you get an inner approximation of the GPT. So here's my preparation device, my measurement device. I'm going to assume the measurements are binary outcome, 0 and 1. And I do a whole bunch of preparations, a whole bunch of measurements, and this is my data table. I'm just keeping track of the 0 outcome of my measurements. So the other probability of outcome 1 is just 1 minus this. So I don't need to keep track of that. So I just have this big data table for the probabilities. And now what I do is I search for a factorization of that matrix into 2 matrices, where the dimensions of these matrices are the number of preparations by some integer k, and then that integer k by the number of measurements. And this integer k is going to just be the GPT dimension. So I basically try different GPT dimensions. I see how well I can fit to a factorization like this. And that fit will be better. You find for which choice of integer k is that fit the best. And you have to consider both underfitting and overfitting. Because obviously, if you make the GPT dimension arbitrarily high, you'll get better and better fits. But then you have tons of overfitting. And so there's kind of tools for figuring out what the optimal choice of k is here. And once you have that factorization, well, now you know the GPT dimension. And moreover, each of these rows can be interpreted as a GPT state vector. And each column is just a GPT effect vector. Notice they have the right dimensionality. And when you take the inner product of a row with a column, by construction, you reproduce the empirical probabilities. So it's a really simple argument. They did the experiment in this paper. They did a bunch of preparations and measurements on a qubit. This is the reconstruction they got with, I think, 100 states and effects. If you do even more states and effects, you start to get even closer to the what you expect, the block ball and the corresponding 4-dimensional object. So once you have this GPT characterization, if you're doing it on a macroscopic object, it may no longer look like the quantum state and effect space, but whatever you get, you just ask yourself, is this GPT a simplex in its dual? Does it fit inside them? And if not, then you falsified macrorealism. So some advantages of this proposal over the prior ones: you don't need to assume non-invasivity. You don't need to be able to prepare pure states. In fact, you don't need to know anything about which states and effects you're preparing a priori. You get that out of the analysis. You don't need to know the number or the nature of the macrostates in advance. You get a full characterization of the operational theory, not just kind of a single witness that you're checking, is it violated or not. Here you get the whole state and effect spaces out. And furthermore, you can use the same data, namely the shape of the GPT, to decide if your system is non-contextually explainable as well. So you can, I'll come to that in the next half, or the final few slides of my talk. And I just had an idea while preparing this talk. Essentially, the problem of falsifying macrorealism is how do you self-consistently get information about states and effects? It strikes me that self-testing is also a way of kind of getting self-consistent information without assuming anything about the states and effects. So maybe you could make proofs of the failure of macrorealism built around this instead of theory-agnostic tomography. But I haven't really thought about it yet. OK, so final topic. I just want to point out the connection between these two notions of classicality. And so what is generalized non-contextuality? It's a notion of non-classicality introduced by Rob Speckens, which, given any theory or set of data, you can use this notion of non-classicality to determine in a principled way if there's a classical explanation or not for that theory or data set. And there's a bunch of motivations for this notion, which I'm just going to skip over. I've given plenty of talks on this. If you're interested, we can talk about it. And as for the definition of non-contextuality, I'm going to skip over the sort of first principles definition that refers to ontological models and so on. And I'm going to instead use just a nice geometric characterization of this notion that we introduced here in the framework of GPTs. So what we showed is that an operational theory is non-contextual if and only if the GPT describing that operational theory is embeddable in one of these simplicial GPTs that I introduced earlier. So what do I mean by simplex embeddable? Well, intuitively, if this is the simplicial GPT we saw earlier, this is a simplex embeddable GPT. It fits inside. Formally, you've got to have linear maps from the state and effect spaces into the state and effect spaces such that probabilities are preserved. And the unit is preserved, I think. But intuitively, it's quite intuitive. It's kind of like a subsystem of a simplicial GPT. All and only these GPTs correspond to non-contextual models. And hopefully it's kind of intuitive. These GPTs are ones for whom the states and effects are a subset of those in these strictly classical GPTs. So it kind of makes sense that these would be classically explainable. But I want to note that it's not completely trivial. Like, notice that if you're saying that the world is described by this blue GPT, you're explicitly forbidding the possibility of this state, for example, and this effect, which are outside the blue GPT, even though they're totally logically possible. So this is analogous to what Rob has called an epistemic restriction, right? It says you can never have perfect knowledge. For example, knowing that it's exactly this classical state is forbidden in this blue GPT. So these simplex embeddable GPTs can be thought of as epistemically restricted classical statistical theories. And we say that these GPTs are classically explainable because you can still imagine that there are these true states of the world. It's just that you're not able to perfectly prepare or measure or know what those ontic states are. But you can still take the ontology to be exactly the same as in the simplicial theory. And an example of this is Speckens toy theory. I'm over time, so I'm just going to jump to this figure, and I'm going to say, here's the simplex, which embeds Speckens toy theory. You construct Speckens toy theory by just taking the midpoints of these edges and then taking the convex closure. So Speckens toy theory is explicitly a simplex embeddable GPT, and these vertices of the simplex are like the ontic states in the theory. Okay, so now we see the relationship between macrorealism and non-contextuality. For a given dimension, there's exactly one macrorealist theory. It's the simplicial theory. But there's many, many non-contextual theories, all of those which have convex geometry fitting inside the simplicial theory. One example of a non-contextual theory in that dimension is the simplicial theory itself, because of course a simplex embeds in itself. But then there's also all these other examples of non-contextual theories. So it's a much broader class of theories than the macrorealist theories. And as a consequence, that's why this class of non-contextual theories can reproduce a large amount of, a lot more phenomenology than the macrorealist theories. So, we can get things like interference and remote steering and key distribution and all these things in one of these non-contextual theories, but not all of those features arise in the macrorealist theory. So it's a much broader class of theories. If you have all theories, the non-contextual theories form some subset, and the simplicial theories are effectively a set of measure zero in the set of non-contextual theories. So what this means then is, at least if you buy the fact that macrorealism and non-contextuality are both well-motivated notions of classicality, then it's clear that a violation of macrorealism establishes a kind of weak form of non-classicality, but a violation of non-contextuality establishes a much stronger form of non-classicality. You rule out a broader class of theories. And notice that theory-agnostic tomography, once you have figured out what the GPT is describing your system, that same data lets you decide if you're exactly where you are in this space. So it also lets you decide if you're outside the class of non-contextual theories, as well as if you're outside the class of simplicial theories. They're both just geometric questions about the GPT. And in particular, notice also that any violation of generalized non-contextuality, so if you know you're outside this set, well, then you know you're not strictly simplicial. So if you've done this with a macroscopic system, then you've falsified macrorealism. So you can repurpose all your proofs of contextuality now to also be proofs of the failure of macrorealism. You just have to make sure the system involved is macroscopic. Okay, so summary slide. We have now kind of a classification of GPTs. We have the strictly classical ones, which if they're macroscopic, we call them macrorealist. We have the classically explainable ones, which are non-contextual. And then we have the genuinely non-classical GPTs, which can't be embedded in a simplex, things like quantum theory. And these exhibit contextuality. That's all I wanted to say. Thanks. Yeah, this is a good question. So the this kind of case you're saying, yeah. So it's a good point. If you when you go and do theory-agnostic tomography, there's always kind of a question of what's the scope of states and effects you do. Like in the experiment that I showed you, they kind of used their knowledge of quantum theory to target, to keep the states and effects confined to a qubit. If you're working with a system about which you kind of have no information about what to target, then you might struggle to get as clear a characterization. But notice that even if you're targeting certain states and effects, you still don't put in, you don't say like, oh, this is a particular state or effect in your analysis. You still can extract the characterization out rather than assume it. So maybe what I want to say too.
The point is like you want to argue that you cannot fit that into a simplex. Let's say you can always fit that into a simplex by putting extra macro states that you didn't take into account. Yeah.
So that's not quite right, and the reason is because I've kind of on many of my slides I've only shown the state space, and that is a bit of a cheat. Really, you have to look at simultaneously embedding the state and the effect space. So even if you've only probed, say, the two-dimensional part of this simplex, it's still possible to, within those fixed dimensional constraints, to get joint states and effects that can't embed in a simplex. So for example, if you take the block ball, you might think you can always embed it in a larger simplex of some size. If you kind of just take the simplex to be big enough, the block ball will fit inside it. But taking the simplex so I haven't talked about the kind of freedom in specifying the relative state and effect spaces in a GPT. So if you take the state space and you shrink it, then the effect space will grow correspondingly because the set of logically possible effects for a kind of smaller set of state vectors will be larger. And so, so I don't think I'm answering very clearly, but so even if you don't sort of probe all the macro states, as long as you stay kind of within a fixed dimension, so within, say, 2 macro states, you can, say that the true experiment has 3 macro states, and let me think how I want the example to work. Say the true theory is a qubit, and you do a set of states and effects which are living in a 2-dimensional space within that qubit. Even though you're not accessing all the dimensions, so there is another macro state, another perfectly discriminable state, if you nonetheless reconstruct the qubit as your state space and the sort of corresponding effect space for the effects, then those will not embed in any dimensional simplex taken jointly. And you don't need sort of to flesh out the full qubit state space in order to see that. So there are kind of nuances here about the problematic case is not when you've failed to recognize an additional dimension. The problematic case is when your states are actually going in that dimension, whereas your effects are not probing that dimension. When there's a mismatch between the dimensions that your states and effects probe, that's the kind of loophole in theory-agnostic tomography. And it is a valid loophole, and it's one that people think about and worry about and have tried to kind of address. But I think for now it is a genuine loophole. But notice that it's a strictly less bad loophole than the one needed for. So the loophole in the case here required you not only to confine your states and effects to the same dimension, but also to reach all the way out to the pure states. So I agree that this is like the frontier for making the loopholes even weaker, but I think it's a strictly less bad loophole than what goes into these experiments.
Suppose that I give you a device and I ask you, is this macroscopic realistic or not? And then actually the device is a classical computer with a lot of processing power. They simulate in a qubit. You would pass your test,
The answer is yes, but it's a clear textual simulation of the qubits.
Why is it weird, right? I mean, I'm giving
have
you
to
a
decide whether that's
physical
weird.
system. It's no weird. I can construct it, right? I mean,
Yeah, but it has been constructed, so you kind of fine-tuned your system, your classical system to resemble quantum statistics, and you
Yes,
can always
yeah.
do that.
Yeah.
But it's like, if you go out in nature somewhere and it looks like qubit statistics, then it would be weird to expect this fine-tuning to begin with. That's, I think, some arguments that in the background always. That's,
man can give you another complicated mechanical system that gives you the same outcomes.
yeah.
Yeah, it's also why you can't use this to rule out for like security reasons compared to locality where you can make security arguments. Because it's not like fine-tuning can also be malicious manipulation to make sure you get the statistics that trick you into thinking you're content.
You can write an iPhone app where you have two iPhones and they
No,
simulate the
you
sharing
cannot violate
signals.
inequality.
Huh?
You cannot violate inequality.
Yes, you can if they signal.
You signal, yes, then you have to experiment in a particular way so that you can signal. That's why.
It would be a
But then,
particular
I
function.
don't know, it's like this thing, this notion of Leggett, right? I mean, it seems to try to rip off the inequalities without using the inequalities, right? I mean, it's like a race that really has no end, right? I mean, because there's no way, right? I mean, you can do it. You really need to separate things, you want to be really sure.
Yeah, if you space like separated, then.
And if you don't, you cannot be sure, period.
So the way I would put it is there's kind of a spectrum of device independence. And at the purest end of device independence, there's no one, not even Bell. So you can't device independently determine whether or not two events are space-like separated. You need some theoretical assumptions, some experimental assumptions to verify sort of space-like separation. But we all agree that Bell is very far along the device independence end because to determine if two events are space-like separated, we think we have a good handle on that. It seems like a very weak assumption.
But it's not theory. Using
sorry.
a different theory. Like using like
Yeah.
macroscopic assumptions, right, to verify something. Yeah, that's
Right. It's appeal to other theories and other theoretical assumptions rather than kind of quantum-specific ones. But I think it's still somewhere on the spectrum. It's not all the way at the like purest end. There's no physics is ever totally.
Matrix and matrix is a classical computer simulating everything as if you were quantum, right? And of course you cannot discard this possibility, right? I mean,
Yeah. So I would say both tests of macrorealism and tests of non-contextuality make causal assumptions. They're just ones that can't be justified by appeal to relativity theory. So the causal assumption is something like that you have some primitive notion of a system and you know how to probe that system. And this is certainly more device dependent than Bell's notion, where you don't need to know what the systems are, you just need to know something about space-time. But I don't think I think once you take the GPT perspective, it's less of a theoretical, it's a less problematic assumption. Like, yeah, assuming that you know how to probe kind of individualized degrees of freedom is a much weaker assumption than assuming all of quantum theory, for example, or even assuming that you know what a particular state or measurement does. But it is.
If you can probe all the dimensions, right? I mean, that is fine, right? I mean, I don't think you have finite dimensional systems in nature, really. It's not even realistic. I don't know.
Okay.
I think this discussion can be in relation. I think the only answer to, in my opinion, to what he's saying is about say the simplest explanation possible, right? Because I'm going to make this the question I wanted to make because I think it's in relation, not because all we are talking whether is what you are experimentally testing and doing tomography with ends up being a simplex or not, but this has to do with the smoothness of the space you find. I mean, if you're having a finite set of experimental points, you will never find smoothness. You can always fit whatever finite set of points into simplest. But I think
No, so yeah, I want to stop you there. So this goes back to what Matthias was asking as well, and I didn't answer very clearly. So what I wanted to say is, once you...
From a very principle, I'm talking very like mathematically. I mean,
Sure. And I'm saying even mathematically, I disagree. And the reason is, it's my fault. I haven't been clear that when you formalize simplex embedding, it's not just a question of embedding the state space into a simplex, but you simultaneously need to find a linear map which embeds the effect space into the dual of the simplex. And that's where it's the joint constraint which can't always be satisfied. So quantum theory is an example of a GPT which you can't find a pair of linear maps which takes the state space into a simplex of any dimension and the effect space into the dual of the simplex, even if you discretize it. Even if you take this approximation of quantum theory where it's totally polytopic, you still can't embed this into any simplicial theory of any dimension. And the reason is because basically if you make the block ball small enough to embed into a simplex, or alternatively you make the simplex big enough to embed the block ball, then you find the effect spaces have to change in a corresponding manner to preserve the probabilities such that they won't be embeddable. So, yeah.
And you can find that thing you're putting, you could find these out of an experiment.
That's right. This is experimental data.
Say, okay, there's no possibility.
Exactly. Yeah, so simplex embeddability is highly constrained.
This could be an answer to what Miguel is saying, right? Because any computer will have a finite, maybe huge, but finite resources. But then, no, it's the other way around, right? Because then even with finite resources, you could, that's strange to me, because even with finite resources, you could be able to simulate something that is contextual. It's not macrorealist. So with a finite computer with finite resources, you should be able to simulate something which is not macrorealist.
Yeah, that's certainly true.
Then it's the other way. I thought the outcome was going to be that, but it's the other way around. But then, I don't know. I still can't see why, but I will need to understand the argument in detail. But I don't think that it's.
Yeah.
In principle, I can't see how you can prove a smoothness of whatsoever out of a finite set of data.
Well, you can't prove smoothness. I'm just saying being smooth or polytopic doesn't have much impact, really any impact on whether or not a simplex embedding exists. So the crux of what makes simplex embedding hard, whether or not you're smooth or whether or not you're continuous or polytopic, the thing that makes simplex embedding difficult is, say I take quantum theory and I try to embed it into, remember the embedding has to be into the states and the effects. So one way to embed the block ball into this geometry is just take the block ball and shrink it a bunch, and then I can fit it inside here. But when you shrink the block ball to preserve the probabilities, you're kind of subnormalizing things, so you need to supernormalize the effects, and now the effect space is not going to embed in this object. Or the, yeah.
Yeah, even a square state space can be embedded in this way.
That's right.
Because the embedding must be linear, for example, as in the background. So operational equivalence is on your square. Mixing these 50-50 or those 50-50 giving the same, they would have to be preserved in the classical theory. And this is hard to do in general.
Yeah, unless you remove some measurements, right? Then you embed it in the
Yeah.
you have to remove measurements, and you remove just enough measurements to make it non-contextual, essentially.
Yeah, that's not linear.
Yeah, so all these questions are about the joint geometry of state and effect spaces. And at various points, I've cheated a bit by just showing you the state spaces because the effect spaces are harder to draw.
Then because I thought all the thing about is trying to find like a non-polytope thing that you can find, okay, this is a block sphere, therefore you don't have like, but if it's more like,
Yeah.
Thanks.
Maybe we run out of time. Just one final question that I'm curious about. So when you now pull out any paper and they say, oh, I tested Leggett and Garg inequality in this and that specific system, oh, it's violated, right?
Mm-hmm.
We agree that there's not so much to conclude from that, but when would you now, your proposal give, say, let's do instead of that experiment, let's modify the experiment a little bit, and then it will actually certify contextuality, and then it would be an interesting result, for example.
Mm-hmm.
Or would you have to redo the experiment completely in terms of theory-agnostic tomography to do so?
Yeah, I suspect it would take more. There might be like a middle ground that's less than theory-agnostic tomography. So like if you were testing non-contextuality, I'm not even sure there's a middle ground, to be honest. I mean, if you can verify your operational equivalences somehow, then you can test non-contextuality. But when you're kind of pushed, okay, how did you verify those? You either had to assume something about your measurements or states, or you had to do a kind of self-consistent analysis like theory-agnostic tomography. So, I mean, I will say that when I kind of started this project as a, one section in another paper I was trying to write where I just wanted to point out how bad the claim was that macrorealism is violated by violations of Leggett Garg inequalities. But then when I went through it all, I had to change my mind. I was like, it's not as, like the assumptions going into the theory-dependent assumptions going into these arguments that Leggett and Garg use are not entirely unreasonable. Like, I do believe in locality. I'm happy to grant that. And I think it's plausible to ask about the space of models which have only two macrostates corresponding to the position of the particle. Clearly, I don't think that's the only interesting or some fundamentally privileged class of models. So I'd rather look at other classes of models like non-contextual models. But I don't think they were unreasonable to consider these. So I guess, yeah, from my perspective, we learn a little something. I'm happy to, for the sake of argument, think about this class of theories where you know exactly what the macrostates are. But if you want to do better and not assume this, then I guess I don't see anything short of theory-agnostic tomography that could, yeah, so I do kind of feel like those experiments probably would have to be redone if you wanted to kind of remove these assumptions from the argument.
Okay, so great. There will be more opportunity for discussing later. Looking forward to that. So let's stop here for now and go for lunch, I think. So thanks again for the nice talk.